Hi, hello everyone. Welcome to this masterclass channel. In this lecture, we are going to discuss about Fourier series. So, what is Fourier series? So, here the Fourier series representation of a periodic signals in terms of frequency components are given. So, that is x of n, which is equal to summation. The limit varies between k equal to 0 to p minus n. So, xk e to the power of ik omega naught n. So this is the definition for Fourier series. Okay, so here for discrete time signal, I represent here n domain, here omega naught. So this omega naught, which is equal to 2 pi by 2 pi fn. Okay, so here if you consider this any periodic signal, this x of n is a fundamental period of capital N. If there exists in convergence series, then this series is called as Fourier series. If there is exist in a convergence series, then the series is called as Fourier series. See, this is the Fourier series representation for periodic signals for continuous time, because Fourier series it can be represented in two types. One is continuous time Fourier series representation and another one is discrete time Fourier series representation. So this one it represents continuous time Fourier series representation. This one it represents discrete time Fourier series representation. Okay, so here x of t, which is equal to summation k equal to minus infinite to infinite xk e power ik omega naught t. So this is the difference between continuous time and discrete time. So we get the Fourier coefficient as follows. Here xk, which is equal to, suppose we find out the frequency component. Okay, the formula is inverse Fourier series, that is xk, which is equal to 1 by p summation n equal to 0 to p minus 1. Then this x of n will comes into inside your summation x of n e to the power of, now your exponential will become negative, that is decaying exponential, minus ik omega naught n. So this is the similar, this is Fourier transform, this is the inverse Fourier transform. Okay, if you want to obtain the time domain representation, you can use this formula. If you want to get frequency representation, you can use this formula. So likewise, similarly for continuous time representation, here you can using the integration, because as we know, for discrete time you are using the summation part. For integration time, you can using the integration part. Okay, so the representation for continuous time is x of t. Here, continuous discrete time is x of n. So other than that, the remaining things are same only. Okay, so the complex exponential Fourier series are represented as a sequence of complex numbers representing the frequency component omega naught k. Okay, this complex number omega naught k is the complex numbers representing. This one is representing frequency component. Okay, so next we move on to what main purpose of the Fourier series, why we need the Fourier series. Okay, I will give the main purpose of the Fourier series. Suppose the Fourier series is used to analyze the periodic signal. First thing is used to analyze periodic signals. Second thing is the harmonic constant of the signal is analyzed with the help of this Fourier series. Second point. Then third point, Fourier series can be developed for both continuous time as well as discrete times. So these are the three main purpose we go for Fourier series. Why we need Fourier series means, first thing is Fourier series is used to analyze the periodic signals. Okay, so periodic means you all know about that. In previous lecture, I will give you more explanation about the periodic signal. If you want to know about the periodic signal, you just go to that video. For that, you need to subscribe this channel. So next, second point is the harmonic constant of the signal is analyzed with the help of this Fourier series. And third one, Fourier series it can be developed for not only continuous time as well as discrete time also. Okay, then now depending different types of Fourier series. Okay, so depending upon the representation, our Fourier series can be represented in three forms. One is trigonometric Fourier series and another one is compact trigonometric Fourier series or polar Fourier series. Then third one is exponential Fourier series. So mainly based upon the representation is split up into three terms. One is continuous time Fourier series, trigonometric Fourier series. Then another one is compact trigonometric Fourier series, or you may call it as polar Fourier series. And the third one is exponential Fourier series. Okay, so now Here I will explain about the trigonometric Fourier series, first representation of your Fourier series. Okay, so how it can be represented here? X of t, which is equal to, okay, a naught. So a of 0 or a naught, you may write down whatever else. Okay, a of 0 or a naught. I am using the slide pointer option 10. Okay, so you may use here a naught instead of a naught. You may use right like this also, a of 0. Okay, plus you add one summation term here. So summation k varies between 1 to infinite. Okay, because already you take down a naught is come out outside. So here our k varies between 1 is start from 1 to end up with infinite, because infinite Fourier series. So inside you can write down ak cos k omega t plus bk sin k omega t. It means you may write down like this also, a of k. So for instead of this you write down a of k cos k omega naught t, cos k omega t, plus likewise here b of k. Okay, you put here naught also, omega naught. Omega naught is the angular frequency. Okay, so write down or say a reference trigonometric Fourier series can be represented like this: x of t, this is your time domain signal, so which is equal to a of 0 plus summation k equal to 1 to infinite a of k cos k omega naught t plus b of k sin k omega naught t. So Fourier series is it's a complicated waveform analyzed into a number of harmonic related sine wave and cosine wave function. Okay, so mainly it consists of two functions. One is sine function and another one is cosine function. So these two functions are represented and to analyze the harmonics. Okay, so any complicated waveform you can easily analyze it into number of harmonically related with the sine term and cosine terms. This is the main purpose of Fourier series. So next thing is Dirichlet's conditions. Before seeing into the Dirichlet's condition, okay, here we are going to discuss about next two representation. Okay, after that we will go into discuss about Dirichlet's condition. Now first thing is over. So what about a of k and what about a of 0 and b of k? Yeah, so here a of 0 it can be represented as a of 0, which is equal to, okay, 1 over the period t, that is 1 by t, capital T. Time t, capital T is represent time period, fundamental time period. So this is for continuous time representation. So I represented in terms of integration form. So integral over the period of fundamental period, that is t. Okay, your mark. Then here inside the term you put here x of t. X of t. So our integration is with respect to t. So I put here dt. Okay, so a of 0, which is equal to 1 over the period of t. So integration over the period time period. So inside you can write down x of t into dt. This is the a naught. Okay, so what about a of k? A of k. So a of k, it represents the cosine function, isn't it? A number of harmonically related with the cosine function. So a of k, which is equal to okay, so here 1 by t, no, now you put down 2 by t. Now you put down 2 by t, 2 over the period of time t. So for continuous I represent as here integration term. So integral period over the period of t. Then so here inside the input term is x of t. So I write down here x of t. This is our input signal. So it should be multiplied with the cosine function. So a of k is always depend upon cosine function. So cosine cos. Okay. So here where is what is that frequency component is omega naught k, isn't it? Omega naught k is the frequency component. So omega naught k, then t. So our integration is with respect to t. So I put here dt. So here I put dt. So this is what a of k value. So okay. Next, what about the b of k? So b of k, which is equal to, here I write down b of k, which is equal to same formula. Here also 2 over the period of fundamental time period t. Okay, so here integral. So integration period is with respect to t time period. So I write down here t. So inside you put input signal, that is input signal is continuous time signal x of t. Then it is multiplied with the sine function, isn't it? So sine function means here you have sine. So sine k omega naught t, that is omega naught k angular frequency multiplied with t. Our integration is with respect to t. So I put here dt. Okay. So this is the trigonometric Fourier representation. So here here all this term consists of integral over the period of t. Okay. So it means the integration over the one time period. So this part it represent, okay, it indicates the integration over the one time period. Okay, this one. So what about here omega naught? Here omega naught, which is equal to 2 pi f. You know that formula. Omega naught is nothing but angular frequency. Isn't it? Omega naught equal to angular frequency 2 pi f. So omega naught equal to 2 pi f. What about f? F which is equal to 1 by t. So formula it become 2 pi. The reciprocal of time period is fundamental frequency. So 2 pi by t. Okay. So where t is the period of the signal of x of t, given x of t. Okay. This form of Fourier series is called as quadrature Fourier series. Quadrature Fourier series. Okay. Trigonometric Fourier series or quadrature Fourier series. Okay. So first formula is x of t, which is equal to a of 0 plus summation k equal to 1 to infinite a of k cos k omega naught t plus b of k sin k omega naught t. It means it consists of two harmonic function, that is sine function and the cos function. Okay, where a of 0, which is equal to, write down this formula, 1 over the period of t, x of t into dt. For continuous time I represent integration. Suppose if you take the discrete time representation, you put here changes into integral become summation, t domain become n domain. Okay, next what about a of k? A of k, which is equal to 2 by t integral over of the period of t, x of t input signal multiplied with the cos function. So here b of k is input signal multiplied with the sine function. Okay, so this type of form of Fourier series it represents as quadrature Fourier series. So next one, trigonometric form of Fourier series. Okay, so this is nothing but compact form. You may call it as it is a compact form for the trigonometric Fourier series, or you may call it as polar Fourier series. Other name for this one is compact trigonometric or polar Fourier form series. Okay, if the two fundamental components of a periodic signal, okay, so b1 cos omega naught t, one is b1 cos omega naught t plus c1 sin omega naught t. Okay, this one is two fundamental component of periodic signal. So then there suppose if you want to add these two, okay, it can be expressed as by trigonometric identity formula. So x of t equal to a0 plus summation k equal to 1 to infinite. So here you write down square root of bk square plus ak square. So for that I represent 1 by 2. Okay, ck cos k omega naught t minus pi k phase angle. Or you may write down a of 0 plus summation k equal to 1 to infinite bk square root of bk square plus ak square. So ck cos k omega naught t plus pi k. So here plus pi k, here minus pi k, because it is represented as expressed in terms of trigonometric identity formula. Okay, so it means the trigonometric Fourier series can be represented in compact form. Okay, in compact form. So that's why we call it as compact trigonometric Fourier series, or you may call it as polar Fourier series. Okay, how to represent compact form? So the same formula I just modify here. So here a of 0 no. So for that I will represent it. Otherwise you may write down like this also. Okay, one more definition I will give here. Same thing only, representation is only vary. Okay, don't get confusion. So x of t, so which is equal to, okay, d of 0, or you may call it as a of 0. Both are same only. So d of 0 plus sigma, that is summation k equal to because here frequency component is only having, so for that k equal to 1 to infinite. Already take down, substitute k equal to 0 value here. Okay, so it starts from k equal to 1 to infinite. So inside the term you write down d of k multiplied with the cos function. First term is represented with the cos function. So I write down here cos function. So cos of k omega naught t, This formula is very easy for you, for convenient for you, because it is that's why it represents compact form. So plus pi of k. Okay, easy way we have memorize this formula. So no need to have any confusion in this formula. Okay, so it's compact method. Okay, it can be represented in compact form. That is x of t, which is equal to d of 0 capital D. This one is d of 0 plus sigma k equal to 1 to infinite. So here d of 0. So here you substitute d of k. Okay, cos k omega naught t plus pi k. Actually, the formula is k equal to 0 to infinite only. Okay, so you substitute, you bring out d of 0 is outside of the summation. So inside you have, you start from 1 to infinite, cos of k omega naught t plus pi of k. So it is called as compact Fourier series, trigonometric Fourier series, or polar Fourier series. Okay, so what about this d of 0? So where d of 0 is nothing but a of 0. Okay, so already you know that a of 0, which can be written as 1 over the period of t, this one, 1 over the period of t, x of t into dt. Okay, this is the d of 0. So what about d of k? This is a new term now. So d of k, which is represented as this portion. So this portion, d of k is represented as this portion. Okay, so it means square root of bk square plus ak square, that is d of k. So remaining one more term, we have pi of k. It means phase angle. So pi of k, it can be represented as pi of k, which is equal to minus negative form. So minus tan inverse of open the bracket, write down. Here we have two coefficient now. So b of k divided by a of k, because here we have two coefficient, that is b of k1 and another is a of k. So b of k by a of k Okay, this is the formula used for to calculate the pi k value. Okay, so this entire representation is known as compact trigonometric Fourier series. Okay, x of t, which is equal to d of 0 plus summation k equal to 1 to infinite d of k cos of k omega naught t plus pi k. So here d of 0 is nothing but a of 0. Already you know that formula, a of 0, which is equal to 1 over the period of t, integral 0 to t, that is x of t into dt. Then d of k is nothing but square root of b square plus ak square. So pi k is tan inverse of b of k by a of k. Next form is exponential Fourier series. Okay, so exponential Fourier series we already given. Okay, first starting itself I will explain about exponential Fourier series. So this is the exponential Fourier series. X of k, which is equal to 1 by t or 1 by p. 1 by p integral 0 to p x of t e power minus j k omega naught t into dt. This is the represent form. This form of representation is known as analysis equation. This one is, we called it as analysis equation. Suppose in this one, x of t, which is equal to summation k equal to minus infinite to infinite x of k e power j k omega naught t. Okay, this is synthesis equation. So this form of representation is known as synthesis equation. This one is analysis equation. Okay, so this is what we call it as exponential Fourier series. So here x of k are called Fourier series coefficient. X of k is Fourier series coefficient. X of t and x of k. So x of t and x of k. This one, it represents Fourier series pairs. Okay, Fourier series pair means when you take the input signals, when you take the Fourier series pair of x of t. Okay, x of t. This is Fourier series pair. It becomes x of k. This became x of k. Okay, so when you take the Fourier series of x of t, we can get x of k. Fourier, so this one is represents Fourier series pair. Fourier series pair. Okay, so these are the formula. So this one which represents as synthesis equation. For this one it represents analysis equation. Okay, so this entire structure we call it as exponential Fourier series. So far we have discussed about three different types of representation of Fourier series. First one is trigonometric Fourier series representation. Second one is compact trigonometric Fourier series representation, and third one is exponential Fourier series representation. Now we move on to Dirichlet's condition. Okay, with this I end up with this video. Okay, Dirichlet's condition. So the Fourier series is a convergent if the signal x of t satisfies this condition, some condition. Okay, so those condition we call it as Dirichlet's condition. If any signal, that is x of t, satisfy some condition, okay, convergent to some condition, those condition we call this Dirichlet's condition. So we can have the four different types of conditions are given in this slide. Okay, if it satisfy this condition, now generally our Fourier series is convergent at this point only. Okay, the first property is single valued property, and second one is finite discontinuities, and third one is finite peaks, and fourth one is absolute integrability. Okay, let us see one by one. What is single valued property? Okay, suppose if you take the signal x of t, this is your input signal, isn't it? X of t, continuous time representation. Okay, now this x of t must have only one value at any instant. Okay, it will have only one value. Okay, x of t which must have only one value at any time instant within the interval t naught. Within the interval t naught. This is very, very important. Within the interval t naught. So within the period, our x of t must have only one value. Okay, at any time instant within the period of t naught. This is what we call it a single valued property. Consists of single value, one value. Okay, once I repeat, x of t must have only one value at any time instant within this interval of t naught. Second property is finite discontinuities. So here the same x of t should have finite number of discontinuities. So if it is satisfied this condition, we call it as Fourier series Dirichlet's condition. Okay, finite number of discontinuities. So in the interval of t naught, because our signal can be represented mathematically. We want to any signal, if you want to represent it in terms of mathematical function, okay, our x of t should have finite number of discontinuities. So this is the condition for finite discontinuities. Third one is finite peaks. So finite peak means the same x of t should have finite number of maximum value and minimum value in the interval of t naught. Okay, finite number of maximum value and minimum value. Finite number of maximum value and minimum value. Third one is absolute integrability. So the signal x of t, the same signal x of t, okay, should have absolutely integrable. Absolutely integrable. It means so integration of, okay, here I write down modulus of x of t, okay, is always less than infinite within the limit. Okay, so in the period of t naught. The period of t naught, I represent here in the period of t naught. Okay, so this is the absolute integrability condition. Okay, the signal x of t should have absolute integrability. So if this above all these conditions are sufficient, but not necessary condition for Fourier series representation, because most of the physical signals are only satisfied this above condition. Okay, so with this I concluded this point video. Once again I will repeat this 4 point alone. Okay, single value property, Dirichlet's condition means single value property, finite discontinuities, finite peaks, absolute integrability. So single value property means our x of t should have contain only one value at any time. So in the interval of within the interval, that is t naught. Finite discontinuities means x of t should have finite number of discontinuities. Okay, in the interval of t naught. Finite peaks means the signal x of t should have both maxima period and minima period in the interval of t naught. Absolute integrability means the signal x of t should be absolutely integrable. That is integral over of modulus of x of t less than infinite. Okay. So if you have any doubt, you just drop it in a chat box in this video. Okay. Upcoming video we have discussed about LTA system, that is linear time invariant system. So keep on watching this channel. Daily we have posted some useful tricks and subject related videos. Okay. So if you like this video, you just hit like button and you just subscribe, share this video to your friends, and you just subscribe this channel. Thank you for watching this video. Thank you once again.